It is 2 in the afternoon. You slept a full 8 hours last night. You woke up without an alarm, felt clear-headed through the morning, answered emails, finished a report, maybe even went for a walk. Then lunch happens, and within 40 minutes, something shifts. The room feels warmer than it should. Your eyelids grow heavy. Sentences that were easy to write an hour ago now take 3 attempts. You blame the food. You blame the lack of caffeine. You wonder if last night's sleep was somehow not as good as it felt, but here is the detail that rarely gets explained. This afternoon heaviness is not a failure of your sleep, and it is not entirely about what you ate either. It is the product of 2 separate biological systems colliding at almost the same moment of the day. And most people have never been told that one of them would happen, even if they skipped lunch entirely. To understand what is really going on, it helps to set aside a common assumption that alertness is a single steady resource that simply drains as the day goes on. It is not. Alertness rises and falls in a wave shape across 24 hours, governed by the body's internal circadian clock, the same system that regulates body temperature, hormone release, and the sleep-wake cycle. Sleep researchers studying this clock in tightly controlled laboratory conditions, where light meals and activity are held constant, have repeatedly found something curious. Even when participants are kept awake on a fixed schedule and fed small, evenly spaced snacks instead of full meals, alertness still dips in the early to mid-afternoon. The dip is smaller without food, but it is still there. This tells us that a portion of the post-lunch slump is not caused by lunch at all. It is a built-in feature of human circadian biology, a secondary trough in alertness that sits roughly 7 to 8 hours after the midpoint of the previous night's sleep, regardless of whether anything is eaten. This is the part of the story most people never hear, because lunch arrives at almost exactly the same time as this circadian dip, so it gets blamed for something it only partially causes. The 2 events overlap, and the overlap is what makes the crash feel so dramatic. So the real question becomes, what is lunch actually contributing, on top of a dip that was already scheduled to happen? This is where meal composition enters the picture, and where established nutrition science gives a clearer answer than most people expect. When a meal is high in rapidly digested carbohydrates, refined grains, sugary drinks, or simply large portions, the body responds by releasing insulin to move that glucose into cells. In people with healthy insulin sensitivity, this process works efficiently, but a fast rise is often followed by a comparatively fast decline, sometimes dipping below the pre-meal baseline for a short period. This swing in blood glucose, sometimes called a glycemic dip, has been associated in multiple studies with reduced slower reaction time and a subjective sense of mental fog in the 1 to 2 hours following the meal. A meal that is more balanced, with protein, fiber, and slower digesting carbohydrates, tends to produce a gentler glucose curve and a correspondingly gentler dip in alertness. There is a second mechanism worth understanding, one that comes from a more specific and still developing area of neuroscience. Deep in the hypothalamus, a small population of neurons produces a chemical called orexin, also known as hypocretin, which plays a central role in promoting wakefulness and suppressing the transition into sleep. Laboratory research has shown that these orexin neurons are sensitive to glucose levels. When glucose availability rises, these particular wakefulness-promoting neurons become less active. This is an elegant piece of biology in evolutionary terms. A well-fed organism historically had less urgent need to stay alert and for more food, so a temporary dip in vigilance after eating may have been a built-in adaptive response. In modern life, sitting at a desk after a large carbohydrate-heavy lunch, that same ancient adaptation simply feels like an inconvenient crash. It is also worth being precise about the evidence here. Most of this Orexin glucose research comes from animal models and cellular studies, with human evidence still accumulating, so it should be understood as a strong working explanation rather than a fully settled fact. A related, longer-standing idea involves tryptophan, an amino acid found in many protein-containing foods, which the body can convert into serotonin and eventually melatonin. Large meals, particularly those containing tryptophan-rich proteins alongside carbohydrates, have been proposed to nudge this pathway and contribute to drowsiness. The effect size in real-world meals is generally modest compared to the glucose and circadian mechanisms, but it likely adds a small additional layer to the overall picture, rather than acting as the main driver. Put together, the early afternoon slump that so many people experience is rarely caused by any single factor. It is the circadian clock's built-in dip in alertness, arriving on schedule whether or not food is involved, layered on top of a glucose and insulin response shaped by what and how much was eaten, with a smaller contribution from digestion-related neurochemical shifts. None of these require poor sleep the night before. A person can sleep 9 hours, wake up rested, and still hit a wall at 2 in the afternoon because the wall was never about the previous night to begin with. The real-world consequences of misunderstanding this are easy to overlook because they feel so ordinary. People who interpret the afternoon crash as a personal failing often respond by reaching for large amounts of caffeine or more sugar, which can produce a brief rebound, followed by an even sharper decline later, compounding the glucose swings that contributed to the problem in the first place. Others assume something is medically wrong with their sleep and begin sleeping longer or napping erratically, which can shift circadian timing and make the dip less predictable, rather than more manageable. Workplaces, largely unaware of any of this physiology, schedule demanding meetings and detailed analytical work for early afternoon, the exact window when natural alertness is at its lowest circadian point, then interpret reduced performance as a motivation or attention problem, rather than a biological one. The more useful mental model is to stop treating energy as something you either have enough of or have failed to manage, and instead treat it as a wave, with a predictable low point built into human biology. A low point that meal choices can either smooth out or sharpen. This reframes the afternoon dip from a personal shortcoming into a known, studied, and broadly universal pattern, one that varies in intensity between individuals, but rarely disappears completely, even in people with excellent sleep habits. In practical terms, this understanding points toward awareness rather than a rigid formula, recognizing that a portion of the dip is circadian and will occur regardless of food, allows for more reasonable expectations rather than self-criticism. Paying attention to how different lunches feel an hour or two afterward, noticing whether a particular meal pattern leaves you sharper or foggier, gives each person a way to learn their own response. Since insulin sensitivity and individual glucose reactions vary meaningfully from person to person, scheduling the most demanding detail-heavy tasks earlier in the day when possible and reserving early afternoon for lower-intensity work aligns effort with the body's natural rhythm, instead of fighting against it. None of this guarantees the dip will disappear, and no single change works identically for everyone. But understanding the mechanism turns a confusing daily experience into something explainable. There is a quiet kind of relief in realizing that the heaviness arriving each afternoon is not a sign that something is wrong with you. It is a rhythm that has been part of human biology for a very long time, shaped by a clock running quietly beneath conscious awareness, responding in part to food, in part to light, in part to a schedule it inherited long before lunch breaks or office meetings existed. Understanding it does not eliminate it, but it does change what it means when it arrives.